In this video, we're going to do a sunlight question. A window has a perimeter of 20 meters and it consists of a rectangular window surmounted on one end by a semicircle. So we can imagine a rectangle and then there's going to be a semicircle. Whoop, imagine that was a better looking circle on the top. Now the rectangular portion is going to allow twice as much sunlight in as the semicircular portion. So maybe let's imagine that this semicircular portion is tinted, so only half as much light is getting in there. We want to determine the length and width of the rectangle so that the maximum total amount of light comes in. All right, interesting question. So we start with the diagram. And the top part is tinted, so it allows in only half as much light. Another way of saying that is to say the bottom lets in twice as much light, so we'll say it that way. Now, if there's no issues related to tinting, then the amount of sunlight would be directly proportional to the surface area. In other words, any part of the window would let in just as much sunlight. However, this case does have tinting. So we're going to say that the top part lets in 1 unit of sunlight per square unit of area, and the bottom part lets in 2 units of sunlight per square unit of area. So we're going to be able to say that sunlight is 2 times the area of the rectangle plus 1 times the area of the semicircle. We don't actually have units for sunlight that we're using here. So we're just trying to indicate that in terms of sunlight getting in, the rectangle is twice as important as the semicircle. Okay, now the area of the rectangle is length times width, of course, and the area of the semicircle is pi r squared. Now, the area of the circle is pi r squared, so the area of a semicircle will be 1/2 pi r squared. So the area of the top part, 1/2 pi r squared, the area of the bottom part, length times width. But because this bottom part's letting in twice as much sunlight, we're going to multiply it by 2. And so we're going to come up with our formula 2 times length times width plus 1/2 pi r squared. Now we have 3 variables, L, W, and R. We have an L, we have a W, and we have an R. By now you've done enough questions that you know we only like to have one. So it's very common, as it says in red here, very important point, it's very common in situations where one of the variables is radius and where we want to get all the variables in terms of one variable, that we let everything be in terms of the radius. That's a pretty common phenomenon in these questions. We let R be that ultimate final variable. So looking at this diagram, if I let length be these 2 vertical sides and I let width be the horizontal side, I see that the width is actually equal to 2 times R. You know, that the radius of that semicircle is 1/2 of that width, so width is 2R. That part was relatively simple. Now, we have to determine length also in terms of R. So what we do is we say, okay, we know the overall perimeter of the window is 20. So a length plus 1/2 of a circumference of a circle plus another length plus a width needs to equal 20. We know that circumference of a circle is 2 pi r, so naturally 1/2 of a circumference will be pi r. So what we really have is that 20, instead of saying 2L plus W plus 1/2 of 2 pi r, we can ultimately say that's the same as 2L plus 2R plus 1/2 of 2 pi r, which is pi r. So 20 is equal to 2L plus 2R plus pi r. And that's written down at the bottom of your page. So what we can do now, we're going to try and isolate R. So if we go back, we see that it says at the bottom there 2R plus pi r. Let's call that 2 plus pi times r. We factored out the r and put it on the right-hand side of the bracket. So it's 2L plus 2 plus pi quantity times r. So that's what we've got written here. And we're trying to isolate L, so we subtract the quantity of 2 plus pi times r from both sides. We get this expression here. And now we can say L is equal to that expression divided by 2. Now we can split apart this fraction. We can call it 20 over 2 minus 2 plus pi quantity over 2 times r. And so we're going to do that, and we're going to say that's what L is equal to, and 20 over 2 is equal to 10, so we can say L is equal to 10 minus the quantity of 2 plus pi over 2 divided by r. Now, sometimes a question like this is going to permit us to use rounding, and sometimes it won't. We're going to do it both ways in this video. We'll do method 1 with rounding and method 2 without rounding. So if we allow rounding in this question, then what we can say is that the sunlight is going to equal, as we said earlier, 2 times length times width. That's double the area of the rectangle, plus the area of the semicircle, which is half pi r squared. We're then going to sub in our new expression for L, and we're going to sub in our new expression for W, and we will have created an equation wholly dependent on R. And then what we can do is use decimal approximations here. And after doing a little bit of distributing, distributing the 2 in and distributing the 2R in, we ultimately get that the sunlight as a function of R is 40r minus 10.283r squared plus 1.571r squared approximately. And we can simplify that a little bit further, and we get a nice expression at the bottom there. Okay. Now, what we're going to do next is eventually just determine that derivative, set it equal to 0, and solve for r. So determining the derivative of that expression on the bottom just means we bring the 2 in front, multiply it, reduce that exponent by 1. 40r just becomes 40 when we use the power rule. And we ultimately get that r will roughly be equal to 2.296. That's the value that we get for r when we set the derivative equal to 0. Now let's consider the domain here. Now the minimum r would occur if the circle was minimized. It's conceivable, although it'd be really, really weird looking, it's conceivable to have an extremely narrow window. I'll do my best to draw it. An extremely narrow rectangle with the littlest tiny circle on top with a radius of virtual 0. So it's possible to have that semicircle on top like that. And an extremely long length. So we're going to say the lower limit of the radius of the circle will be 0. On the other hand, it's possible to maximize the semicircle. Now, what would that look like? Well, if we maximize the semicircle, it would mean we were minimizing the rectangle. So we'd have a huge semicircle with the littlest tiny rectangle underneath it. Okay, so let's imagine that that little tiny rectangle on the bottom was virtually 0. That would mean that the entire perimeter of 20 meters was used up just creating a semicircle. Well, if that happened, then what that would mean was that the width of that rectangle, in other words 2r, plus 1/2 of the circumference of the circle, in other words 1/2 times 2 pi r, would be equal to the entire 20. And that's what we've written here. Now, again, what we're doing here is maximizing r for our domain. Well, if that happened, we would get 2r plus pi r was equal to 20, or the quantity of 2 plus pi times r equaling 20. That would mean r was equal to 20 over 2 plus pi. So we would see the lower limit of the domain would be r equals roughly 3.89. I should actually say the upper limit. Okay. So the lower limit would be where r was virtually 0, and the upper limit would be where r was virtually 3.89. Okay, so now using these two values as endpoints of our domain, we see that the r value that let the derivative equal 0 was in fact in that domain. So that's good news so far. And so what we can do is simply evaluate each of these. So let r equal 0, and we'll see that the sunlight coming in would be 0. We don't, as I said earlier, have actual units for sunlight here, but we'll say the sunlight coming in is 0. If we let the radius be 2.296, the sunlight coming in would be 45.914 approximately. And if we let the radius be 3.89, the sunlight coming in would be roughly 23.77. So we would get the most sunlight when the radius was approximately 2.296 meters. Now, the width of the rectangle, if you go back to the question, it said, what are the length and width of the rectangle allowing that maximum sunlight? So the width is roughly 2 times the radius. So 2 times our value for radius of 2.296 would give us 4.592. And the length was given earlier by a formula that we arrived at. So that would make the length roughly 4.097. So to actually answer the question as it was asked, we would want the width of that rectangle to be approximately 4.59 meters and the length to be approximately 4.10 meters. Now, what if we didn't use rounding? So the rest of this is just going to confirm those answers, but again, show you that it's possible to do this without rounding. We already have an expression for L and we already have an expression for W in terms of R. Doing a little bit of distributing, we end up getting an expression for sunlight as 40R minus 2R times the quantity 2 plus pi times R plus 1/2 pi R squared. Okay, well, we want to add these two R squared terms because they're both like terms. So in other words, what we're trying to do is add 4 plus 2 pi, the coefficient of the first term, and that's actually a negative quantity, 4 plus 2 pi. And then we also want to add that to 1/2 of pi. And when we do that, we will have collected the like terms there, the R squared terms. So what we can do is make this have a denominator of 2. And when we do that, we get our polynomial looking like this. And we're going to remember that we need to distribute this minus sign to the 8n to the 4 pi. And so when we do that, ultimately we get that the surface area as a function of r is equal to 40r minus, and then the quantity is 3 pi plus 8 all over 2. And that's the coefficient of r squared. For the domain, again, we want to, for the same reasons we said earlier, the minimum R would occur if the circle was minimized. So that's possible conceivably to think of that as 0. We discussed that earlier in this video. On the other hand, if we wanted to maximize the semicircle, that would mean that the lengths were essentially 0. And so we would have the width plus 1/2 of a circumference equal to 20. And so plugging in a width of 2r and 1/2 times 2 pi r and letting that equal 20, we would ultimately get that r was 20 over 2 plus pi. So the lower limit of the domain would be 20 over 2 plus pi. And so we'd be able to say that this was the equation without using any rounding at all for the sunlight coming in. Now, setting that first derivative equal to 0 would mean that 40r's derivative would be 40. Multiplying 2 times 3 pi plus 8 would, multiplying 2 times 3 pi plus 8 over 2, which is what the power rule requires us to do, ultimately just makes that coefficient 3 pi plus 8. Setting that equal to 0, we would get r is roughly equal to 40 over 3 pi plus 8, and r is roughly equal to 2.30. Now you'll notice I considered decimal approximations here just for a moment. A while ago we said the upper end of the domain was roughly 3.89, and an r value of 2.30 is roughly what the radius should equal. And you might wonder why we're doing that. Well, I just want to make sure that this radius is in fact in the domain. without using decimals, it might be a little bit hard to picture whether the value of 40 over 3 pi plus 8 is actually somewhere inside our domain, which was given a while ago as 0 to 20 over 2 plus pi. So it might be a little bit difficult to see that without using some decimal approximations. Okay, so now that we've got the three values, the 0, and then the value of r that made the derivative equal 0, and the upper end of the domain, we're just going to do some evaluations. Subbing in an r value of 0 is relatively straightforward, and we get 0 minus 0, which is 0. Now, subbing in a value of 40 over 3 pi plus 8, which was the value of r that made the derivative equal to 0, gets us to this point here. So we get 40 times 40 is 1600 over 3 pi plus 8. That's not too tough. Distributing here, we get 1600. And so 3 pi plus 8 times 1600 becomes our numerator. And 2 times 3 pi plus 8 quantity squared becomes our denominator. Okay, well, we can actually do a little factoring up top. We can cross out the 1600 and make it 800, and then cross out that 2 and make it a 1. And we can cross out this 3 pi plus 8 and cross out one of those 3 pi plus 8s. And we actually get this value right here, which is simply 800 over 3 pi plus 8. And that's roughly equal to 45.91. So 800 over 3 pi plus 8 will be the sunlight coming in at the value of r that sets the derivative equal to 0. And then finally, for the upper end of the domain, we plug that value in as well. And again, a pretty similar thing happens. We get a kind of a complicated looking expression, 800 over 2 plus pi, and then we get 400 times 3 pi plus 8 over 2 times 2 plus pi quantity squared. Well, in this case, though, we can do a little simplifying here, make the 400 a 200 and make the 2 a 1. Ultimately, we get to this value. We need a common denominator, so we're going to have to multiply top and bottom of that first fraction by 2 plus pi. And so doing that and distributing the minus sign, we ultimately get a value for the sunlight coming in of 200 pi over 2 plus pi quantity squared, which is roughly 23.77. And so without using any rounding at all, we see that we want the radius to be 40 over 3 pi plus 8. That would mean that the width of the rectangle is 80 over 3 pi plus 8. It's 2r. And then finally, to figure out what the length would be, we use that formula right there. And we do a little bit of multiplication. And we get ultimately 10 minus 20 over 2 plus pi quantity over 3 pi plus 8. We'd like to get a common denominator, so that common denominator will be 3 pi plus 8. And that's what we do right here. And we distribute that first numerator. And then we remember in the next step to distribute the minus sign. And ultimately we get 10 pi plus 40 over 3 pi plus 8. And so the maximum sunlight allowed will be when the length of the rectangle is 10 pi plus 40 over 3 pi plus 8, and the width is 80 over 3 pi plus 8.